talk.
All right, so thanks Moore, and thanks everybody for attending. I'm sorry I couldn't be there in person. So as Moore said, I'm going to talk about discrete log with preprocessing with optimal time-space trade-offs, and this is joint work with Gil. So the discrete log problem is potentially one of the most fundamental problems that we have in public key cryptography. It underlies many cryptographic constructions of signatures, key exchange protocols, public key encryption, short arguments, pairing-based schemes, and much, much more. So we would really like to understand the exact security or hardness of this problem. And traditionally, when we think of the discrete log problem, this is the problem that we think about. So we have our discrete log algorithm A in the middle. It gets as input a description of some cyclic group G of prime order n. It is generated by some generator little g. And it also gets as input an instance H, which is a group element in the group G. And the goal of A is to output some solution X, which is the discrete log of H with respect to the generator G. So A wins if G to the X is equal to H. Now, the assumption that we typically make in some groups is that any efficient, so to speak, algorithm A only has a small probability of winning in this game. And we would really like to instantiate efficient and small with some concrete parameters. So we would like to understand for some fixing of the term efficient, how small exactly is the success probability of the discrete log algorithm. Okay, so in other words, how hard is the discrete log problem? And note that we need to restrict the discussion to some groups, since in some groups, it's an easy problem that we know how to solve very efficiently. Okay, so the best that we can hope for is that the discrete log problem is hard in some groups. And even in these groups, the best trade-off that we can hope for is that the success probability is something like t squared over n, where n is the order of the group, and t is the running time of the discrete log algorithm. And this is the case since we have generic algorithms, so to speak, that succeed in computing discrete logarithms in any group. And this is the success probability of these generic algorithms. The good news is that Shu proved back in 1998 that this trade-off is actually optimal for such generic algorithms that succeed in any group and don't use the representation of the group elements. And in fact, we do have candidate groups in which we don't have any algorithms that perform better than the generic algorithms, and in particular, this is the case for some standard elliptic curve groups. Okay, so this is the picture that we saw before, and this is how we typically think of the discrete log problem. And note that this kind of setting assumes that the discrete log algorithm A learns the group G together with the instance H, right? So it needs to compute the discrete log of H, and it learns H together with the description of G. Now, this is not typically the case, right? So typically in cyclic groups, we fix some group and we work in this group over an extensive period of time. And throughout the time, we learn some instances and the adversary wants to compute the discrete log of the instances. So perhaps a more realistic scenario is the following, in which we have two stages, a preprocessing stage and an online stage. In the preprocessing stage, there's a preprocessing algorithm A0. It gets only the description of the cyclic group, and it outputs an advice string STG. And then in the online stage, we have an algorithm A1 that gets the advice outputted by A0 together with an instance H in the group, and the A1 needs to compute the discrete log of H. Now, this is potentially the scenario that we want to think about, since we want to disallow scenarios in which, for example, a preprocessing algorithm that runs for a long period of time can output a very short advice that serves as a trapdoor to the group, right? So given this advice, A1 can very fastly compute discrete logs of many elements. So this is the scenario that we really want to think about. And now the goal of a discrete log algorithm in this scenario is to optimize the trade-off between three parameters. So on the one hand, we have the success probability, and on the other hand, we have the size S of the advice string and the running time T of A1, so the running time in the online stage. And interestingly, it turns out that this preprocessing does help you. Lior Rotem and Bernstein and Lang gave preprocessing algorithms for the discrete log problem that improve upon the success probability of just online algorithms. And so they succeed with probability, which is roughly S times T squared over N, where again, S is the size of the advice, T is the online running time, and N is the order of the group. And as Pavel mentioned, Corrigan, Gibbs, and Kogan proved a few years ago that this is indeed optimal for generic algorithms. So they gave a lower bound in the generic group model that shows that this trade-off is optimal for generic algorithms. Okay, so it seems like the situation is solved, right? We have a lower bound and a matching upper bound. So what am I talking about? So as it turns out, the algorithms of Lior Rotem and Bernstein and Lang suffer from a small caveat. And the caveat is that these algorithms are non-explicit in the sense that they assume a very long shared randomness between A0 and A1. So what do I mean by that? So this is the model that we considered before. So the algorithms of Lior Rotem and Bernstein and Lang don't really operate in this model, but they work in a model in which the preprocessing algorithm A0 and the online algorithm A1 share a random function mapping elements from G to Zn. So this is the model that we work on, and it leaves open the question of, is there an explicit preprocessing algorithm that doesn't assume such a random function between A0 and A1 that computes discrete logs and matches the lower bound of the Corrigan Gibbs and the Kogan of ST squared equals to epsilon n. And I should mention that in the analysis of the algorithms of Lior Rotem and Bernstein and Lang, we don't really pay for this random function anywhere. So it's not counted in the space of the advice, and you don't really pay for invoking this random function. So you implicitly assume that each invocation of the random function costs you a constant time limit. Okay, so this is the question that we want to answer. And in light of this question, our contributions are the following. So we do present an explicit discrete log algorithm that doesn't assume shared randomness between the preprocessing stage and the online stage. Yet it matches the optimal trade-off in terms of space and time. And so it matches the lower bound of Corrigan, Gibbs, and Kogan. It's generic, so it really does match the lower bound in the generic group model. In particular, it catches the interesting case where both S and T are roughly n raised to the power of 1/3, and the success probability is constant. And I should mention that it also provides tight bounds for the computational Diffie-Hellman assumption or the computational Diffie-Hellman problem with preprocessing in the generic group model, since Corrigan, Gibbs, and Kogan also proved a similar lower bound for this problem in their work. So these are our contributions. And in the time that I have left, I want to talk about the existing approaches before our work for solving the discrete log problem explicitly with preprocessing. Then I'll present the discrete log attack that assumes shared randomness between A0 and A1. And then I'll talk about our preprocessing algorithm, or in other words, how we de-randomize the shared randomness attack. And finally, I'll conclude with a summary and some open questions. So let's talk about existing approaches. So one thing you can do in order to get explicit preprocessing algorithms is simply to not use the preprocessing stage, right? So if you just take any discrete log algorithm, which is explicit, you get an explicit preprocessing algorithm. Perhaps a more interesting thing you can do is you can use fiat and OR's preprocessing algorithms for general function inversion and apply this algorithm to the discrete log problem. So you apply the general function inversion to the function of exponentiation in the group. The inverse of this function is discrete log. So this can be used in order to solve the discrete log problem. These two approaches, however, are suboptimal. I won't go into detail, but they don't give you the optimal space-time trade-off that Corrigan, Gibbs, and Kogan proved as a lower bound for the discrete log problem with preprocessing. And the third approach is to apply the random oracle heuristic to the shared randomness attack that I mentioned before. So in a bit more detail, the idea there is to instantiate the shared random function age, which is shared between the preprocessing stage and an online stage, with a concrete cryptographic hash function. So for example, SHA-256, right? So you take this model in which A0 and A1 share a random function age, and then you instantiate this random function age with a concrete function. So for example, SHA. So this is very similar to what is often done in security proofs in the random oracle model, where you first prove security of a scheme in the random oracle model, and then you instantiate the scheme with a concrete hash function. But though this is similar, it's not the same. It's very different. And I want to focus on two ways in which this is different. So the first is that typically the random oracle heuristic is used in order to argue security. Here it's used in order to argue correctness or to bound the success probability of an attack, which is different. And, it's better in some senses, it's worse in others, but it's fundamentally different. And perhaps worse, what's different is the number of evaluations of the hash function. So typically when you consider security proofs in the random oracle model, you assume that the adversary makes a polynomial number of queries to the random oracle, which translates to a polynomial number of evaluations of the hash function. Here, potentially the discrete log algorithms make an exponential number of evaluations of the hash function, right? So we make a very strong assumption in which SHA, for example, behaves like a random function, even when you evaluate it on an exponential number of inputs. So this is the second difference. And finally, note that using this heuristic somehow unnecessarily ties the concrete security of discrete log with preprocessing to how the concrete hash function that you use actually behaves or mimics a random function, which is something that we typically want to avoid. Okay, so this is the random oracle heuristic and how you might use it in order to replace the shared randomness with a concrete function. So let's present this shared randomness attack. So the main building block of the attack is the random walk on the group elements of G. So the random walk is defined by the following steps. If you're currently in a group element H, the next group element is H times G to the alpha, where alpha is the hash value of H using the shared random function. Okay, so this is a random walk over the randomness of the function H and the starting point, which is typically chosen uniformly at random. So let's see a picture of this random walk. So we start from a random group element H0, then we move to H0, which is G to the X plus alpha 0, where X is the discrete log of H0, and the alpha 0 is the hash value of H0. Then we move to H2, which is G to the X plus alpha 0 plus alpha 1, where alpha 1 is the hash value of H1, and so forth, until we reach some group element HK, which is G to the X plus the sum of all the hash values in between. So two things to note here. The first is that if you know the discrete log of H0, you know X, then you can compute the discrete log of the endpoint, right? So it's simply X plus all the hash values that you observed. And conversely, if you know the discrete log of hk, then you can retrieve the discrete log of h0, right? Because you simply subtract from the discrete log of hk all the hash values of this random walk. Okay, so these are two things to remember. And now we can present the preprocessing attack on discrete log. So in the preprocessing stage, the preprocessing algorithm builds S random chains of length t each using H. So it picks uniformly at random S starting points. And from each starting point, it performs a random walk of length t. Okay, so we have T chains of length, S chains of length t each. And eventually it stores the discrete log of each endpoint as its advice, right? So the preprocessing algorithm was the one to choose all of the starting points. So it knows the discrete log of all of these starting points. So it can compute the discrete log of all of the endpoints. So the advice is simply all of the endpoints plus their discrete log. So this gives us an advice of size roughly S. Now with the online stage, the online algorithm gets this advice as input plus a challenge, an input element H. And the online algorithm wants to compute X, which is the discrete log of H. So what it does, it performs a 2T step random walk starting from H. So it takes one step and another, and hopefully eventually it will hit one of the stored nodes that it got as part of its advice. And if that's the case, then it can compute the discrete log of H. Since we mentioned that the discrete log of this element is included in the advice, and once it knows the discrete log of this element, it can compute the discrete log of H. So this is the attack. And the online running time is roughly O of t because we take a random walk of length 2t. So how do you analyze the success of the attack, the success probability of this attack? So the preprocessing stage touches with high probability at least something like S times T nodes, right? S times T group elements. This is simply a Markov bound. From this, we can conclude that in the online stage, each step that the online algorithm takes hits one of these red nodes with probability, which is at least S times T over N. And overall, we get the probability of hitting one of these red nodes within the first T steps of the online random walk is at least something like ST squared over N. And note that this is indeed sufficient in order to bound the probability that the online algorithm actually computes a discrete log of H, since if the online walk hits one of these red nodes within T steps, it has a budget of another T steps. And so it's guaranteed that somewhere within these T steps, it will hit one of the stored nodes, and then it can recompute the discrete log of H. Okay, so we get that the success probability is roughly S times T squared over N. So let's briefly review our algorithm, how we de-randomize this attack, and with that we'll conclude. So note as a starting point that the previous preprocessing attack only touched, so to speak, at most something like ST group elements. So a standard de-randomization technique is simply to replace this random function with a function which is ST-wise independent, right? And the same analysis will apply. So you simply take this random function, and instead you let the preprocessing algorithm sample f, which is the hash function that now the algorithms will use from an ST-wise independent family. And this f is included as part of the advice, so A1 can evaluate it. The problem is that now we get a suboptimal trade-off. So I won't go into the exact parameters, but I will mention that the suboptimality is inherent. Right, so for any implementation that you choose of an ST-wise independent hash family, you'll get a suboptimal trade-off. Okay, so the first step that we make is reducing the level of independence. So what we do, note that the analysis of the shared randomness attack was somehow global in nature, right? reasoned about the total number of nodes that the preprocessing stage touched. What we'll do is we'll switch to a somehow more local analysis that allows us to reduce the level of independence. So indeed, arguing that there are at least S times T preprocessed nodes does require ST-wise independence, but we don't really care about the number of nodes that are touched by the preprocessing stage, right? What we do care about is the probability that the online walk intersects one of the preprocessed walks, right? The number of preprocessed nodes is just a means to an end. So this is actually the probability that we want to bound. And our main lemma is that if you sample F from something like T-wise independent family, then still the probability that the online walk hits one of the preprocessed nodes is something like ST squared over N, right? And I won't go into the proof. It's by the inclusion-exclusion principle, and you can see the details. Okay, so this is still not enough, okay? Because you still have to pay for each evaluation of this function F in the online running time, and this still results in a suboptimal trade-off between the space, time, and the success probability. And I'll skip this part. Fiat and OR somehow encounter a similar problem. I just want to mention that the way they solve this problem somehow doesn't seem to give us the parameters that we want. So we need to find a different solution. And the solution is to sample F from a family that has weaker guarantees than full-fledged T-wise independence, but on the other hand, has constant evaluation time in the unit cost trial model. So the function family that we use was introduced by Pay and Pay. It's based on cuckoo hashing. So you can think of sampling a function from this family as a two-step process. First, you sample a family from a collection of families, and then you sample a function from this concrete family. And the guarantee proven by Pay and Pay is that if you fix a subset X of group elements in our case, then with high probability, this H is a K-wise independent function on this subset. Okay. So this is what we want to do. We want to use these kind of hash families. The problem is that the analysis of Pay and Pay only tells us that if you fix the subset X and then you sample a family H, then H is fully independent of X with high probability. The problem is that in our analysis, X corresponds to a random walk or concatenation of random walks on G. And so it really does depend on the hash function that you choose, or more generally on the hash family. Fortunately, previous work by Berman et al. Showed that this is still okay. And actually the guarantee of Pay and Pay can be extended to such adaptive settings as well. Okay, so this gives us the bound that we want. Let's just conclude. So we presented an explicit discrete log algorithm that is optimal. It matches the lower bound of Corrigan, Gibbs, and Kogan. It gives us type bounds for D log and CDH. A small technicality is that we do assume that S is at least T in some sense. But I think that we can probably get rid of this technicality rather easily. And in particular, it gets us this nice trade-off of S, which is n to the 1 minus 2 beta, and T, which is n to the beta for any beta, which is at least 1/3. Sorry. And just I won't have time to really go into the open questions. Maybe I'll just mention does this preprocessing algorithms have implications for other data structure problems? So Fiat and OR's function inversion was recently shown to have implications for some preprocessing variant of threesome. So this is a nice direction perhaps. And another is, can cuckoo hashing be used for function inversion? So the bounds of Fiat and OR are somehow non-tight, especially for functions that have many inputs mapped to the same output. So can you use something like the Pay and Pay hashing to improve the bounds in Fiat and OR? Okay, so with that I will conclude. Thank you for listening.
Thanks, Lior. Are there any questions?
Yeah. Sorry, not me with the mic.
I know we're in information theoretic cryptography right now, but we use a PRF to replace this code because and then share E of the PRF.
So I can't really hear the question. Maybe another microphone would be better.
Okay. Can you hear me now? Oh,
Better, yeah, better.
I know we're in information theoretic cryptography, but why couldn't you just replace this random oracle by a PRF and then use share the key between the stages?
So again, you invoke the random function on an exponential number of values, right? So you can, and you'll get a trade-off, under an assumption for a polynomial number of values, right? So for a very short advice, or for an algorithm, a normal algorithm that runs for a very short period of time. But we get something which is first unconditional, and secondly captures the entire interesting trade-off, in which the advice can be exponential and the running time can be exponential.
Okay, thank you.
Sure.
Hi. So can't you use or exploit maybe the randomness in the GGM model itself to solve the problem? Like, if the group is chosen at random, couldn't you kind of emulate a random oracle, or at least put a weaker condition on the function on the function family that you use? You don't seem to need really k-wise independent on this subset, right?
Well, yeah, but how would you instantiate this stack, right? You revert back to the same problem once you assume. So if you're the GGM, again, essentially you assume some source of shared randomness between the preprocessing stage and the online stage.
I mean, the whole thing is in the GGM, right? Or maybe I missed it.
So it's an attack. It can, apply to any concrete group. Right.
You want it to apply to even to worst case, in a sense, kind of type of group. Okay, makes sense.
Sure. Yeah.